Hello everyone. Today we will start new chapter in chapter 9, state transformation. First of all, I want to remind you that to try to help you to remember example 7.4 we did in last week. And in the question I asked stresses in 3 points in the cross section of A prime, and point A and point B and point C. I'm giving the results of two stresses in these points. You can see on point A, we have a maximum normal stress, but on the contrary, shear stress at point A is equal to 0. At point C, we will get to 0 normal stress value. On the contrary, while we have a shear stress on point C is the maximum. On point B, normal stress is not maximum, shear stress is not minimum, but both values and the moderate values. So I'm wondering that which point is the most critical on point A and point B and point C. You can see we can also have a categorize with the point A and point C because we have a normal stress value and shear stress value is directly given. Unfortunately, phone calling phone calling, therefore I need to stop synchronization, recording. Okay, let's continue. I'm wondering that which point is the most critical. Point B, you can see we have a lower normal stress, but also moderate level. So the question is, can point B can be more critical? So just consider stresses on point element B. I said we have a moderate, normal, and shear stress values. So I'm wondering that are the stress values remain unchanged with different orientation. The orientation means that if we rotate infinitely small element B, for example, theta angle, if we get a different normal or shear stress value, maybe in so question answer is no, it changes. The value is changed. So is there any relationship between the indifferent orientation? The answer is yes. How we can find? By using equilibrium. And also I want to make some multiplication. We have a like element B, okay, normal coordinate system, x and y in the coordinate system. If I rotate by theta, okay, and also needs the normal stress and shear stress value, I'm represent as a prime angle x prime and y prime values, and I want to write to like connected to each member, and I want to take a like theta angle by using the geometrical relationship. Okay, by using geometry we can make a relationship between this theta. Okay, I am taking these infinitely small elements and I want to write to forces and normal stresses and forces by using this triangle surface. Okay, first of all I want to define with two areas. I want to, this infinitely small area is delta A. So by using the geometrical relationship, by using the sinus cosine theorem, this should be is delta A times sine theta. This surface, area of this surface should be delta A times cosine theta. Also, I said, we know the stresses on this surface. For example, in this surface, I want to say the sigma x prime. Okay, this surface is the sigma y prime. Sorry, sigma y and sigma x. Also, surface of the parallel stresses on this surface we define as a tau. I can't draw in this place, you know, if you back to the previous slide like this, okay, you can see the values, okay. This prime I can't write on the surface because I don't have enough space. So if I take a relationship, okay, you can see, and sigma fx equal to 0, sigma f5 equal to 0, we will get to two equation. What are the unknowns? We know the, sorry, if I have a pen, I know the sigma x prime and sigma y prime. We know the theta values. We know the infinitesimal delta a values. I can give a unit value, for example, 1. It doesn't matter in the equation. These values can disappear. Okay. After by using it, we have two unknowns. First unknown is sigma x prime. Second unknown is the tau x prime and y prime values. If I two equation, two unknowns, I don't want to go in details. It's just the mathematical calculations. Okay. After summarizing these equations, solving equation system, we obtain two values. Sigma x prime is equal to sigma x prime plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 times cosine 2 theta, tau xy sine 2 theta. Also tau xy equation given like this. Okay. We don't need to memorize, just I want to how we can obtain these two equations. Also sigma y prime is missing in the calculation. In order to get sigma y prime, I'm taking it another triangle, okay, by using this. By using this triangle, okay, also I can get my sigma prime and I can get string transfer equation. These three equations I want to write like this one, and this one is the stress transformation equation for plane members. Okay, plane members is the 2D members. When we can get that, we have a like 2D infinitesimal members. In general, we have 3D infinitesimal elements, but now we're concentrate. First, we start with the plane stress transformation. Plane terms comes from the 2D element. Okay, so first of all, I want to start with this application. How we can solve? Okay, the question. You know, we have a formulation. Write the formulation, apply the formulation, and get the result. Nothing more. Okay. First of all, we start with the example 9.1. It's taken from the Hibbeler. Okay, you can check this example from Hibbeler book. Also, we have an infinitely small element like this. Okay, these dimensions infinitely small. These are the stresses, normal stress and shear stress. First of all, how we can get the value? Okay, before coming to the next slide, I want to write. You can maybe remember that. Also, if you forget that, I can remind you. For example, if our x is like that, this is the x, this is y. Okay, it's if our surface, okay, like this, surface times direction is positive. Okay, surface times direction is positive. Okay, value is positive. Surface times direction is negative, our value is negative. First of all, let's start with a normal stress. For example, in normal stress, I can use different color. For example, green color. Like this section, okay, direction is positive, okay. Surface is also positive x, okay. Direction positive, therefore this value is positive. Okay, therefore I can write the but in this surface, for example, in like this, direction is negative, okay. Surface also is the negative x, okay. The value is positive. Let's start with the normal stress. We can see our normal stress value is 80, but direction like this. Direction is negative. Okay, I can put the clear times reason. Okay, so in this, if I write the sigma, okay, direction is negative because it's negative x direction, okay. To surface is the positive x surface, therefore the surface is the positive. So our value is, sigma x value is negative 80, okay, like this. If you have a, hocam, it is difficult to figure out. If any shortcut, I can say for the normal stress, for shortcut, you know, if our direction is the tension, okay, we can get the positive value. If our direction is the compression side, okay, we can accept it as a negative, okay. It's a shortcut, but I want to give a general relationship. Therefore, I'm writing the direction as surface. Okay, let's continue. And for example, in sigma y, direction as, for example, I want to take this arrow. Okay, in order to equilibrium, this arrow side should be down direction. Sigma y, and 50 value is 50. Look at the direction, and direction is the positive y direction. Also surface is the positive y surface. Therefore I want to put positive. Multiplication is positive, therefore I need to write to 50. Okay, now to complicated term is tau x y, also x surface y direction. Let's continue. Let's start with the tau x y, this one. Okay, the surface is the positive surface. You remember that is the positive surface. This is the negative surface for x. This is the negative surface for y. Okay, this is the positive surface. Look at the direction. You know, direction is negative, surface is positive, therefore tau xy should be negative 25 megapascal. If I have a shortcut, I can help you. Okay, you don't need to memorize. Okay, these direction side for, sorry, this direction for the shear stress we called as the positive. Okay, this side is the negative. Okay, if you confuse, okay, you can use the shortcut like this. Also, I say the compression is negative for normal stress, tension is positive for normal stress. Okay, these are for shear stress. Okay, shear stress direction, magnitude also. Okay, sign. Okay, sorry. Also, this is the normal stress sign. I hope you understand clearly. If you have a question, you can write message on Classroom or also send me as an email. Okay, let's start with, I said sigma x is negative 80, sigma y is positive 50, tau is the negative 25. I write, you can say, okay. So also I want to write two angles. If our angle is counterclockwise, okay, counterclockwise is positive, clockwise direction is negative. Therefore, if question is clockwise, I have to write the negative 30. Clockwise direction is negative, our coordinate system. Okay, let's start our formulation. You know, we have a formulation sigma x plus sigma y plus. I write to a minus 84 sigma x. If I write the 54 sigma y, I didn't write the values. I can write on here. Okay, like 80. This is 50. Okay, like plus 50 divided by 2. Also, this is the minus 80 minus 50 divided by 2 cosine times cosine minus 50. Okay. Also, we write to 2xy, we can write to minus 25 times sine minus 50. We will get this value. If I write this formulation, we calculate the tau. If I put these values instead of this equation, we will get these values. You can see I didn't write two values on hand calculation because it's straightforward. This is so clear. Okay, we have a formulation, we put the values, we get the results, nothing more. Therefore, I don't want to lose time for calculating these numerical I don't want to lose time for using numerical calculations, numerical computations. Therefore, I just write the exact results. Okay. Okay. Also, this is the graphical distribution. It's extremely important. You know, this is the, if I rotate our infinitely small by clockwise direction, I can write the minus 30, you know, minus coming from the clockwise. Okay, our values changes from 80 to 28, 25.8 is decreases. Also, these values is from tension. You can see this is comes from the compression. On the it is both two stresses is decreases. On the contrary, and tau xy values is negative 25, increases from negative 25 to negative 68.8. It increases. So in this case, I can say in some cases, maybe we have got the more shear values, more normal values, normal stress values. So in which case our normal stress can be has the maximum values, in which case, in which orientation we have a maximum shear stress values. It's, I think the next we can pass to the next section. We can call, you know, now we can pass to this section. In this section, we call the principal stresses. The principal stress is this: the orientation, the principal stress. Sorry. Okay. Principal stress is the maximum or minimum normal stresses. Okay, just that. If in which orientation we have the maximum or minimum normal stresses, we can call these stresses is principal stresses. In principal stresses case, okay, our shear stress is equal to 0. So if we calculate normal stresses or principal stresses, when the normal stresses becomes the principal stresses, okay, our tau value become 0. So by using this relationship, we can find the sigma 1 and sigma 2. How we can find? You know, we have a tau xy value. Okay, if I, you know, in special case, okay, I can write is equal to 0 for this formulation, and we can figure out to theta becomes theta p. Yeah, in other words, we can find to orientation of the principal stress orientation or angle. Okay, principal stress angle. So I write to this formulation and we can get to theta 2p. You can see by using this relationship, if I move these values from the left to right, okay, if I divide it by, if I move to cosine to here and this one cosine to here, and I can get tau xy divided by sigma x minus sigma y divided by 2, we can get to tangent theta of 2 theta p. Theta p is the orientation angle of two principal stresses. Okay, if I apply this relationship to this formulation, okay, I don't need to write this. Like if I write to, instead of cosine theta and sine theta for tangent 2 theta p, okay, we will get this formulation. You can see very simple. Maybe some of you can think that, hocam, this is not simple, this is a little bit complicated. Maybe, yes, you are right. But if I compare with the previous formulation, this one is more simple than the standard stress transformation formulation. Okay. Also, I can say you don't need to memorize this formulation. I can give you. Also, you know, we are making an online exam. You can also easily reach this formulation. So don't worry about confusing equations. Okay. Also, you don't need to memorize. Okay. Anyway, let's make a practice for new example. Okay. We have a poor torsion system. When the torsion is applied to this bar, maybe you can remember from the chapter 5, I think that I can't exactly, poor torsion. When you poor shear stress can occur, how we can compute it? You maybe remember that tau is equal to T times J times C. Okay, so in this case, there is no normal stress occur in this system, just on shear stress occur in this system. So if I take any part of the system, we have an infinitely small system. We have like per torsion tau like this. Okay, so what book needs, or what we need from this in this question, determine the principal stresses. So you know, there's no stresses, normal stress occur, but in some orientation we have the maximum normal stress value of normal stresses. They're asking that, in other words, sigma 1 and sigma 2 is needed. Okay, also find the principal stress orientation angle, in other words, theta p is needed. So we have a formulation, we apply the formulation. First of all, I want to start with the tangent 2 theta p. You can see 2 divided by sigma x and sigma y. First of all, what is the value of the sigma? What is the sigma x? Sigma x equal to 0. What is the sigma y? Sigma y is equal to 0. What is the value of tau xy? Tau xy is equal to minus tau. You remember, this is the minus side. That when I look into direction, I can write the minus tau. So I write to tangent 2 theta p. You can see I put the minus in here. Okay, so I write to minus 2, and 0 divided by 2 is equal to 0. 2 divided by 0, I get the negative infinity. So in which angle tangent 2p is infinity or negative infinity? Maybe you can remember that, you know, tangent is asymptote for when the angle is 90 degree. So 2 theta p is equal to 90, so, or minus 70. So theta p can be 45 or 135 degrees. So we found the orientation. Now I can pass to the sigma 1 and sigma 2 equation. You know, if I put the values, 0 for sigma x, 0 for sigma y, this is a 0. Okay, this is 0. So now write to minus tau. So if I take a square, therefore it doesn't matter, and minus or positive, therefore sigma 1 or sigma 2 is equal to 2 and minus 2, like this. Okay, it's very simple, but I want to start with the 45 degree. So in geometrical, if I try to make a pure tension, we have a crack as like 45 degree. So maybe we can figure out that in the when we have a pure torsion, okay, our beam or our bar can crack for 45 degree, because you know the weakness orientation, the most weakness orientation is 45 degree. Therefore, in this case, our bar cracked on make a angle like 45 degree. Okay, so there's a important reason why our angle like the 45 degree. Strange. Okay. So first of all, I want to pass to maximum in plane shear stress. Okay. What is the meaning of the maximum in plane shear stress? In plane meaning that to 2D. Okay. So don't worry about in 3D. Maximum shear stress is a little bit different. You will see the next week, maybe next lessons. Okay. So first of all, you remember from the high school, you know, the maximum meaning that derivation of some function with respect to the some parameter, it should be equal to 0. So in this case, we have a tau because we are wondering the maximum shear stress. And of this system depends on the theta, depends on the orientation. So I need to take a derivative of the tau with respect to the theta, okay, is equal to 0. So you know we have a formulation tau like this. If I take a theta, to take a derivation, this formulation with respect to theta, I don't want to lose time for mathematical calculation. Maybe you can remember that. What is the derivative of sine 2 theta? We can calculate, okay. Though, you know, I don't want to lose time. After calculating this, okay, we get these, you know, sine 2 theta is 2 cosine theta. 2 sine theta is 2 cosine theta is minus 2 sine 2 theta. Therefore, is minus minus. Okay. Also, I want to make some parameter. For example, this parameter moving to the right side. Okay. And if I divide it by cosine 2 theta, we obtain the theta sine 2 theta s. Theta s means that the special case, special orientation of the when the maximum in plane shear stress occur, okay, minus sigma x minus sigma y divided by 2 tau xy. It is very similar to theta p. You can see in this case we get to positive tau xy divided by sigma x sigma y divided by 2. Okay, in this case, now we take a reverse thing. Very strange. Also, we have a minus in here. Very strange thing. Okay. Also, if I apply the formulation from the R sigma x and sigma y values, okay, I don't want to write the sigma and sigma x, sigma y s. Maybe I can write sigma 1s and sigma y, and we can, in this case, we get to do just on the formulation. If I apply this to general formulation, not like this one, okay, we will get this term is disappear. Where is it? I'm going so fast, sorry. This term and this term is gonna be disappear. Okay, just only this term is remaining. Therefore, sigma xs and sigma ys is equal to sigma average for when the maximum in plane stress. So when the our shear stress is maximum, we can't say normal stress is equal to 0, but we can say normal stresses in both x and y axis becomes equal, and this is also equals to average stress. Average stress meaning that to sigma x plus sigma y divided by 2. Okay, so if I apply this system to tau xy value to this orientation, okay, so tau maximum is becomes 2 and sigma x minus sigma y divided by 2 square plus tau xy square value. So this is our formulation. Okay, let's do it practice with the example. Now it is a different example. We have a axial loading system. When the axial loading, you remember that we have a just only normal stress occur, okay? And we have a one direction axial force, therefore just only x direction we have a value, and I want to call this as a sigma, okay? We have a tension force, therefore we have a tension normal stress, you remember that. And also we can say sigma x is equal to, sigma is positive, okay? Sigma y is equal to 0, so no shear stress, so tau xy is equal to 0. So if I compute, and question is, but question is, when the axial load is applied in this figure, it produces the tensile stress in material, determine the maximum in plane shear stress. So there's no shear stress, but in what orientation you can see some kind of shear stress can occur. In which case, let's continue. So I write the values in here, okay. When I write the value to in here, so sigma x equal to sigma y is equal to 0, so this value is become to minus sigma divided by tau is equal to 0, so we get the negative infinity. Similarly, to example 9.2, theta s is equal to 45 degree or 135 degree, okay, again 45 degree, very strange. So if I apply in the tau max, okay, so sigma minus 0 divided by 2 squared plus 0. So we get to positive sigma divided by 2 or negative divided by 2. So value is half of the sigma. Also, in this case, our average value, okay, on sigma in this orientation, also we have a sigma value, normal stress value. This value is also equal to sigma average is equal to sigma over 2. So graphical illustration of the system, you can see sigma over 2, like this, okay. Again, we get this 45 degree. Is there any geometrical representation in system? Yes, again 45 degree. Hocam, how we can compute this? For example, okay, if you, okay, apply system, okay, sometimes we have a crack like 45 degree. Again, for example, if I beam and if I put a point load, there is a pure bending. You remember that in pure bending, okay, we have a normal stress can occur, okay. We have a crack like 45 degrees like this. Maybe in some slides you can see, if I have pictures like this, if I put like pictures, I can't remember. I didn't put, but maybe you remember from some kind of the structures. Maybe when you look at the balcony, sometimes you can, for example, if you have a balcony like this, okay, we can see some kind of the cracks like 45 degrees because, and if crack on 45 degrees, okay, our toe is plane and we have a see cracks when there are beams on 45, I'm sorry, when the angle is 45, okay, our beam can crack due to shear stresses. Therefore, 45 is extremely important in our question. Okay, so hopefully you understand. I think that we can stop for this week. Okay, first of all, I want to apologize. I want to apologize because yes, tomorrow we have a lecture. Okay, I want to finish this video about 2 or 3 days ago, but unfortunately I don't have time. Sorry about that. Okay, hopefully you have enough time to watch this video. If you don't have time, okay, if you don't have time, I can't do anything. Okay, next week maybe we can discuss about this chapter. Okay, see you later. Bye bye. Okay, let's continue with the more circles of plane stresses. First of all, I want to rewrite to general representation of the principal stress. You already know how we can calculate the sigma 1 and sigma 2 values by using sigma x and sigma y and tau xy values. Maybe you can remember that function values. Just I want to focus on this equation. What is the geometrical meaning of this equation? First of all, I want to symbolize this term as A, also sigma minus sigma x and sigma x minus sigma y divided by 2a, I want to present as a B. And I want to tau xy term, I want to represent tau xy term as a C. After adding that, after this symbolization, okay, I obtain this function. Sigma 1, 2 is equal to A plus or minus in square root B square plus C square. So what does it mean, this value? Just try to, I want to draw a shape of this diagram. How is it I can share like this? Also, I want to write the tau maximum in plane, maximum shear in plane. Stress value, you can remember that. Again, tau x and minus tau y, sigma x minus sigma y divided by 2. It's also I symbolize to remember that as B. So B square plus C square. So first of all, I want to start with that function in square root B square and C square. It's this function is the circle function, like R square is equal to B square and C square. So if I want to draw a circle, okay, and and B is the, for example, horizontal value, C is the vertical value, and R is the diagonal value. You remember that using the Pythagorean theorem, B square plus C square in square root equal to R. So if I want to draw an whole position of the B and C, we can obtain a circle. Maybe you can remember from high school. Okay. So, and also, what does it mean that I can symbolize this equation as a circle? And name of the circle is one of the cited. Symbolize this equation as a circle function, okay, and solve our problems by using the geometry equation. So maybe I can continue from the formulation. You remember that the theta p is the orientation of the principal stress, and tangent to theta p is equal to C divided by B. In other words, if I want to focus on this angle, you can see this angle represent to, in the circle, this angle represent to principal stress orientation angle. Okay, so if I want to focus on this, I can say that sigma 1 and sigma 2 is equal to A, while minus and positive, plus or negative, R, and also the R is equal to B squared plus C squared, tau x minus is equal to R, and tangent 2 theta B is equal to C divided by B, and tangent 2 theta S, I forgot that, not E, is equal to minus B divided by C. Maybe you remember that theta S is equal to orientation of the maximum in plane shear stress angle. Okay, so remember where A is equal to sigma sigma x plus sigma y divided by 2, B is equal to sigma x sigma y divided by 2, C is equal to xy. Maybe if I write these things, you can see, this is difficult thing, because so we try to just only symbolize the formulations. Also, we can directly, why we are directly why we are giving up using directly equation. Drawing circle, it seems to be a little bit harder. Maybe you can think, but if I use the maybe in next step I can show it that by applying this strategy you can see solution of finding solution strategy to find two principal stresses or maximum in plane shear stresses. By using this strategy it's very easy if I compare with the using two functions. Okay, first of all I want to write like a pseudo code of to how we can find the circle or how we can find two sigma 1 sigma 2 so maximum values by using more circle. First of all we draw a sigma tau coordinate system. Sigma represents the x direction, tau represents the y direction. Then we have 2 points. First point is the sigma x minus tau xy. Okay, we marked first of all, just marked this point on the coordinate system, and also we marked second point is which means that sigma y tau xy. Okay, after that we draw a solid line to linear line between 2 points. In this line represent the diameter of the circle. Okay, after drawing the diameter of circle, okay, we obtain to do we can directly find to do draw the more circle. I think that this I can use to my whiteboard to easily figure out. Okay, let me 5 seconds to open my camera. Okay, I think you can see my whiteboard. Okay. Now I want to use this point in step by step. It's much more easier. First of all, I need to look at in first step, we are drawing to sigma tau coordinate system. I say the x coordinate represented by sigma, y coordinate is represented tau. Okay, this is sigma tau. Step 1 is completed. Then we mark 2 points. Just anywhere I can like, for example, tau xy, I say sigma x is positive, sigma y is the negative value, for example. So tau xy, sigma xy. First point is I want to look at this. Tau xy negative, tau xy sigma x. So like this, minus tau xy sigma x, and this is the first point. Okay. Then second point is the negative part. Sorry, as also I said, the sigma y is negative. I want to write sigma x like this. On the screen, I can write sigma x minus tau xy. Okay, and also I want to write to sigma y positive tau xy. This is my second point. Okay, and I merge these two lines. Okay, this r is the represent to diameter of the circle. Okay, this point is the center of our circle. Okay, now I can draw a circle. I'm not good at for drawing circle. Hopefully I can draw. Yeah. Yes, very well. So after drawing circle, to calculation is very easy. First of all, I want to radius of the circle. You know, I said the centroid of the coordinate of the centroid is sigma x plus sigma y over 2. Okay, location of this. This location is sigma x minus sigma y divided by 2. Okay, so this value is the 12xy. Okay, by using Pythagoras theorem, we can find, you know, I want to write to diameter, symbolize diameter, and this is the radius. Radius is equal to in square root. This value I remember that I can symbolize with b and c. Okay, b squared plus c squared. This is the third step. Then after that, this from adding from point C to this value to R value, we obtain this is sigma 1 and this is sigma 2 values. And tau xy is equal to R values. I think if I make a numerical example, you can easily figure out the values. Okay? So let's start with continue with the example. First of all, read the example. Due to applied loading, okay, axial loading and moment, we have like on point A, we have infinitely small element. We obtain these internal stress values, okay, and 12 megapascal and 6 normal stresses, 6 megapascal shear stresses. The question is, first of all, determine the principal stress using Mohr circle, determine the maximum in-plane stress in Mohr circle, determine the principal stress orientation angle, in other words, theta p, using Mohr circle. First of all, try to remember the direction of the infinite of small elements. I want to do like this part. First of all, what is the meaning of these values? You remember that is 12. I don't need to write 2, sorry. I need to move this value like this. Okay, 12. And these are 2, 6. So also this direction is 12, 2. Also this direction should be 6. So you remember that I assume that this direction is x direction, the up direction is y direction. You can see sigma x should be inverse to the direction, therefore I went to negative to that value. In other words, this is compression. Okay, this is positive or negative, this is negative. How can I remember that? You can see multiply with the surface, surface is positive, direction is negative, y direction. So surface direction x is positive, but y direction is negative, so tau xy is the negative 6. So what is the sigma y? There is no stresses on y direction, therefore sigma y is equal to 0. So I recorded 2 stress values on infinitely small element A. Now we can pass to do our Mohr circle. First of all, I want to draw 2 sigma 2 diagram. Okay. First of all, I want to pick first point. You can remember that sigma x negative tau xy. So first point is negative 12. Negative tau xy is the positive 6. So I want to mark the negative 12. Okay. Then positive 6. And this is my first point. Okay. And my second point is sigma y positive tau xy. So second point is 0 minus 6. So this is minus 6. This is 0. So this is our second point. So I need to merge these 2 points. This is the diameter of our circle. What is the center point location is? Maybe you can easily find. This is the 0, this is minus 12, therefore this should be minus 6. So centroid of the circle is minus 6. Position is minus 6. Now I am also, this value is 6. This value is 6. Therefore, this is 6 square root 2. Okay. So, R is equal to 6 squared plus 6 squared is equal to 6 times square root 2. So, I already found R. This is also, you remember that, to maximum in plane. So, if I want to draw the more circle like this, inshallah, hopefully, I can draw a good circle. Okay. Yes, it's okay. It's acceptable. Okay. So, my total maximum in plane is equal to 6 times square root 2. I think I can calculate using my calculator, or I can copy and paste looking for the results. Where is it? This? Yeah, 6 times 49. I'm sorry. 6 times 49, and I need to find, yes. So this is equal to 6.49 megapascal. So this is a sigma 1, or I can write in sigma 2. It doesn't matter, sigma 1 and sigma 2. Okay. Sigma 1 is, I think I can write like this, that value is sigma 1. It's up to changing it, which one is a sigma 1 and which one is a sigma 2. It's up to you, okay? So this is the first point, okay? If you consider to orientation of the principal axis from this angle, okay, I can define this point is sigma 1, okay? If you think I want the orientation angle like this, okay, so I can write this point as a sigma 1. Which one do you prefer? It's up to you. I don't want to handle with big angles, okay? So I want to, this angle is the orientation angle, so 2 theta p in here, okay? So this angle for me is the orientation angle, okay? So theta p is equal to, in this angle, so sigma 1, I want to obtain sigma 1 is like this. How we can find the sigma 1? Sigma 1 is equal to minus 6, from this point, adding to radius minus 6.49. So I obtain minus 14.49 MPa, megapascal, is the sigma 1 value. Okay, so sigma 2 is equal to, minus 6 plus 849 minus, sorry, not minus, positive 2.49 megapascal is sigma 2. Okay, now I can calculate with the theta p. You can see tangent to theta p is equal to, you can see this value. What is this value? You can remember that positive 6 divided by this value. It's also, this is positive or negative. I can say this is the negative value. Okay. It doesn't matter positive or negative. It's actually it's important like that. This is the second degree. I'm going to do from C to here. I'm going outside, therefore I write the positive. I'm going to do negative x direction, therefore I write negative. You can see this is the -1, and -1 meaning that when the tangent 2 theta p is the -1, that's meaning that the 2 theta p is equal to -45 degree. Okay, so, or sorry, 2.5 degrees, so this is equal to, and we obtain theta p is equal to -22.5 degree. Okay, maybe you can write the 135 degree. It's up to you, but I say that I'm always talking about this angle. Okay, therefore this angle is 45 degree. Okay, I hope I am doing correctly. Let me check that. This is the counterclockwise. Counterclockwise is the positive. It should be positive. Maybe I can write the positive 6. I don't want to confuse in case positive 45 degree and positive 22.5 is, I think, that much more easier. I don't want to handle with the positive and negative things. Okay, this one is okay. So you can see this is actually maybe I can control with my formulation. Maybe I made a mistake. Actually, yes, I made a mistake. This should be minus, and this should be positive. Yes, I made a mistake. Sorry about that. Okay, let's go back to the here. Okay, this is the positive minus, so this is positive 45, positive 22.5, positive meaning that this direction is counterclockwise. Sorry about, maybe I can check to do my angle like this. Okay, so by using Mohr circle, sorry that maybe you didn't see my correction. Okay, so we found the orientation of the angle theta p, we found the tau max value, we found the sigma 1 and sigma 2 values by using Mohr circle. And by comparing using two functions, I think that this strategy is much more easier for you, much more easier than the previous strategy, in my opinion. It's up to you. You can use both the formulation strategy and Mohr circle strategy. For me, it doesn't matter. Just only in the exam, I need to find principal stress, maximum in plane shear stress. Now I can pass to next example. You can see angle here. And in this example, we have again infinitely small element like this. Again, in the example, the principal stress needed using Mohr circle. Also, maximum in plane shear stress is using the Mohr circle. And in this point, we need to orientation of the theta as value. Okay, let's start. First of all, I need to delete this part first to clean the surface. And I think you didn't see my whiteboard. I need to open my whiteboard like this. Okay. Okay. I need to look at my infinitely small elements here. I can use this space like this. Okay. This one is the 20. This one, this value is no. The angle is reversed. Sorry, that. Change the arrows. Like this arrow. This arrow is 60. This horizontal value is 90. And I don't know to rewrite. This is 60 and this is 20. Okay, so first of all, I want to write the value of sigma x, sigma y values. and twice y values. This is x angle, this is positive y angle. Okay, you can see sigma x is reverse to the x angle, therefore I write negative 20. Sigma y, you can see the tension, so I can write 90, you can see, okay. And tau xy, the surface is the positive, dimension is the positive, therefore tau xy is the positive 60. And now we can solve now we can find principal axis using motion circle. First of all, I need to draw through sigma, so coordinate system. First point is due sigma x minus tau xy. So sigma x is minus 20, like this, okay. Tau xy is 60, but we are wondering that the minus 60, therefore I can write like minus 60, and first point is minus 20 minus 60, okay, like this. Sigma y, this is the first point. Second point is the sigma y. Maybe I can write the sigma y like this, a little bit harder, like this. It's okay. This is 90, and also positive tau xy, so positive tau xy like this. Okay, this is our second point. Second point is 90, 60. Okay, now I can combine these lines. Okay, and this is the center, and location of center is, you can see, 90 minus 20, 70, and half of the 70 is 35, 35, 0. Okay, this point is 35. So that's meaning that this length is 90 minus 35. I can calculate this, 55. Okay, and you know this length is 60. So R is equal to also tau maximum in plane is equal to square root. Okay, I think I can shift my whiteboard like this. Okay, in plane is equal to square root 55 plus 60 is equal to, I don't want to use my calculator. I can look at my slideshow. I think that's okay. 81.4. So I can use 81.4 megapascal. So I want to draw a circle. Okay, I can't have enough space to draw a little bit this circle, not like this. Like this. Sorry about the bad circle. Okay, so this value is equal to maximum is equal to 1.4 megapascal. Okay, so I find to R. Now I can easily find the sigma 1 and sigma 2. You remember that if you want, we can going back to this angle to calculate the 2 theta p. Okay, I need to delete this part. Okay, two strategy we have. Maybe we can rotate from here to here. So I can calculate 2 theta p in here. It's up to you. Or you don't need to use the 2 theta p in here. You can use 2 theta p like this. It's up to you. Again, I want to handle with the small angles. Therefore, I want to write to this angle 2 theta p. You remember that. First of all, tangent 2 theta p is equal to minus, remember this is the C, this is the B, okay, minus C divided by B. C value you can see going to the down direction, so in order to see, I want to write the negative 60. Okay, so B is also in here. Negative value is negative 60 divided by negative 55. So negative 60 divided by 55. So after that, we obtain 2 theta B is equal to. I don't have a good calculator. I need to use my calculator in here. Where is it? Is this angle is 2 theta. Oh, sorry, we are not handling with theta p. Sorry, that the question is the 2 theta s. In order to use theta s, we need the angle. Just we need to like this angle. So they are wondering that angle. So in here, this is the 2 theta s. We are not wondering the theta p. So tangent 2 theta s is equal to x b divided by c. B is equal to going to this direction, so this value is positive 55. Okay, so also this, sorry, I'm sorry, negative 55, going to the from here to here, negative 55. Also, this value is going from here to here, so this is the negative 60, and after 60 is positive. Sorry that. Okay, phone calling. Sorry about this. Okay, so didn't see the screen. Sorry, this. Okay, going back to the screen. Okay. Now I need to rewrite again. So, what is the meaning if the theta s? Theta s is this angle. So I need to measure values. So from the value you can see this dimension is going this direction, therefore this is the minus 55. This is going to the down direction, therefore I need to write to the negative 60. So tangent to theta s is equal to minus 55 divided by minus 60. By using trigonometric relationship, theta s is equal to 21.3 degrees. Okay, this is the theta s. Now finally I can find the sigma 1 and sigma 2. So if I use these directions, sigma 1 and sigma 2 is okay, but I want to theta s, theta p like 2 theta b in this angle. So I'm defining sigma 1 in here, sigma 2 in here. So sigma 1 is equal to 35 minus, what is the maximum? 1.4 is equal to, I'm not good at in calculator, but 30, I think that minus 56 point, no, not 56, 46.4 megapascal. So sigma 2 is equal to 35.81.4 is equal to 116.4 megapascal. This is the sigma 1 and sigma 2 values. Let me check our results. Oh, sorry that I miswrite. This is not. I think I made a mistake in here. Actually, this is 51. I think something is wrong that. This value is not correct, okay. I made a mistake. This should be 35, okay. And this should be 35. So this value should be 46 and this should be 116.4. Okay, let me check the book result, but in my opinion this one is correct. Okay, I'm sure that because this should be not minus 55, this should be minus sorry, not minus 55, this should be positive 55 degree. Okay, let me control. Okay, this calculation is wrong, I think that. Okay, also I want to use the Mohr circle using the circle transformation, plane stress transformation. I want to use one more example for Mohr circle transformation. Okay, I think we can stop in here. I think that also maybe I can show the strategy. Okay, you know, plane stance transformation use Mohr circle. It's when you look into this screen, this seems to be complicated, but it's not complicated. I promise that. Okay, for example, we have a sigma x, sigma y, and tau xy. Okay, we are drawing our Mohr circle by using this angle. Okay, so first of all, we find the theta p value. Okay, by referencing theta p value, by measuring the theta p value, okay, then we can find the reference of the second angle. This is the subtraction from the real angle to theta p value angle. Okay, then we found this angle. I symbolizes the theta prime p value. Okay, by using this value, we can pass to the sigma x prime and tau xy value. Okay. So first of all, we drawing also strategies. First of all, we start with the similarly to previous strategy, draw a coordinate system, mark 2 again, and drawing the Mohr circle, calculate the theta p. Then we found to the 2 theta p, 2 prime, the theta prime p value. Okay, after drawing the 2 theta p value, we are calculating the B prime and C prime values by using trigonometry. Okay, then we mark to the second point and we found to the sigma x and tau xy and sigma y values. Okay, I think this example is a good practice. Actually, I have time. Okay, I can solve. Maybe I can increase it with my speed. Okay, let's start with the and plane stress is giving like this. I want to write drawing to do. Okay, you didn't see my whiteboard. First of all, I want to showing my whiteboard like this. Okay, here, very well. In here, we are into the small element. This is 8. This one is 12. Okay, and this one is 6. So sigma x is equal to minus 8, sigma y is equal to 12, tau xy is equal to minus 6. Okay, so what is the question? If two element orientated 30-degree counterclockwise, so theta is equal to, counterclockwise is the positive angle, so theta is equal to 30-degree. Okay, and find to do sigma x prime, sigma y prime, and tau x prime, y prime value. Okay, let's start with the drawing our Mohr circle. Okay, I'm going a little bit fast. Okay, this is my sigma tau coordinate system. First point is sigma x minus tau xy. Sigma x is equal to minus 8. Okay, tau xy minus tau xy. Therefore, I can write minus positive 6 because minus positive. Therefore, this is my first point. Second point is sigma y. Sigma y is the 12, like this. This is positive 12, and So this is the minus 0.5. This is my second point. Okay. So I can combine two lines. Okay, like this. This is the center. What is the value of center? Sum this value. 12 minus 8, 4, divided by 2. This is the value, point is 2. So this dimension is 10, is also 10. Okay, you already know this value is 6. Okay, 6. So by using this, r is equal to e square root 6 squared plus 10 squared. I don't need to calculate, I need to look at to the slideshow. Okay, 12.22. Let's control was no 11.66. So this is r is equal to 11.66. So I need to make this part. Okay, so I need to go to more simple. Okay, like this. I don't need to find the sigma 1 and sigma 2 values, just only I know r is equal to 11.66. So also I need to find the theta 2 theta p angle. You remember that the tangent 2 theta p is equal to minus, and this is c divided by p. So c is minus, c is positive 6, b is the going to the reverse direction minus 10. So this is the positive. So what is the 2 theta p? I need to search my angle. 2 theta p is equal to 96. So after that, I found 2 theta p is equal to 30.96. So I found 2 theta p. You remember that we have a theta, so 2 theta p prime is equal to 2 theta p minus 2 theta. So in other words, geometrically I can show you. You know, I need an extra color pen, but I didn't have. I can find it. Okay. Like this is my second line. Oh, thank you so much. This is 2 theta p. You already know, but I need to delete this part. This is the theta, so 2 theta. Okay. You know, just I'm wondering this angle is equal to 2 theta prime. Okay. So I need to find this. You can see this is the 30.96 minus 60. So after that, I think that 29.04. I think that. Okay. This should also negative. So negative meaning that it's clockwise direction. So you can see this angle is clockwise direction. Okay. So 2 theta p angle is clockwise direction. I think you can see. Okay. So now I can find the values. So maybe I can clean and I can focus on shape. You know, I can show you. Okay, this is the centroid. Okay, you know this length is r is 12.699. Okay, you know this is 2. Okay, so this angle going to be reverse. This angle is 29.04 degrees. Okay, so I can measure this value and this value. How is it that? This is the, I can show you, this is the C prime is equal to 12.66 plus multiply by sine 29.04 degree. This is the 11.66 multiplied by cosine 29.04 degree. Okay. So I can check to this value. What is that? This value is 10.22. Okay. Which one is 10.22? Yes, cosine is 10.22. Okay, so what is the sine value? Sine point, where's my sine point? Oh, sorry, just only sigma x, y, sigma x prime and y prime value. Okay, first we will start with this point. Okay, 10.22. So this is equal to 10.22. So you can see this is the 0.1, therefore I can write to sigma x prime. So sigma x prime is equal to 2 minus 10.22. Okay, so I obtain minus 8.22. Okay, the other part is the sigma y part. So sigma y part is 2 plus 10.22, also 12.22 megapascal. Okay. So also tau value is needed. So tau x prime, y prime is equal to, I can't calculate, need a calculator. Hopefully I will calculate that. Let me check. Haha, I didn't calculate. No, I calculated in here. 5.66. So this value is 5.66 value. Okay. So x prime, y prime value. Okay. Hopefully you understand. Okay. Oh, sorry. You did my whiteboard. Okay. This vertical direction is 5.66 value. But this value, it should be positive, not negative value. I think I made a mistake because no. Yes, it should be value is not negative and should be positive. Okay. I can correct the formulation in the slideshow. Okay. I think that sign is negative. Yes. I think that should be in here. It should be negative value available in here. Let me check and control. Okay. I can find. Okay. Anyway, yes, it's similar mistake on principal stress formulation. I forgot to write minus in here. Okay. Also, by using two more cycle strategy, you can easily figure out because first point is the sigma x prime minus tau x prime. So this value is the minus, therefore tau xy should be positive. Therefore, this value is positive 5.66 value. I hope you understand this question. Also, we have enough time to make more practices. Okay. Next subchapter is the absolute maximum shear stress. I will planning to continue next week. Okay. See you later. Okay. Hello, everyone. Let's continue with the chapter 9.5, absolute maximum shear stress. This is the last chapter, is last subchapter in our section. Okay, let's continue. What's the meaning of absolute maximum shear stress? Always up to this subchapter, we are always considered the plane stress. What does it mean, the plane stress? We are considered the stress transformation on 3D dimension. However, in general case, okay, Even there is no stress occur on Z direction, 3D dimension. Also, sometimes in some cases we need to consider 3D cases. How I am trying to explain. For example, if I have a plane stress elastic, for example, we have the sigma 1 and sigma 2 values, and both values is positive. Okay, so we consider the maximum in-plane shear stress is equal to the average of these stresses. No, sorry, subtraction of these stresses. I miswrite in here. Okay, but sometimes but if we consider to the 3D case, that's meaning that if we're in 3D case, we have also additional stresses in Z direction. Also, we know that the Z direction is equal to 0. So in this case, in 2D case, in 2D case, we are just only considering the circle, but in 3D case, there's an additional circle available in from sigma Z and sigma 1, and that is a big circle. If you consider the big circle, you can see, also I want to make a zoom like that. Yes, this one is better. Okay, so if we consider just only 2D case, we are just drawing two more circle. Also, you can see the tom value is smaller than the big circle. So we should consider to 3D case even our stresses occur on 2D dimension. Okay, so we need to calculate to maximum shear stress, 3D absolute maximum shear stress. How we can calculate it? It is very simple. Just you can see, we know, I want to zoom again this more circle. If I want to zoom, if the radius of this circle is half of the sigma 1, so I can easily write maximum in-plane stress is sigma 1 divided by 2. Also, my assumption is sigma 1 is bigger than the sigma 2. So if you say sigma 2 is bigger, also you can change the formulation as sigma 2 divided by 2. Okay, it's very simple. Also, you can see sigma multiplication is greater than 0. Now I want to focus on these assumption, these case, okay, this criteria, okay. But in some, okay, sorry that I forgot to write. No, yes, I write, but I forgot to writing that. You can, some of direction is, for example, sigma 1 is the one direction is positive, one direction of the stress is negative, for example. For example, sigma 1 positive, sigma 2 negative, so multiplication becomes negative. In this case, our Mohr circle change, I'm sorry that, no, not like this. Where's my, yes, I forgot to write, yes. I put a different Mohr circle, sorry that. I need to change this one to this one, okay. In this case, you can see the size of the big Mohr circle change is not sigma 1 over 2, sigma 1 plus sigma 2 divided by 2. So in this case, if the multiplication of the sigma 1 and sigma 2 is lower than 0, our maximum in-plane shear stress, not in-plane, to maximum absolute maximum shear stress is sigma 1 plus sigma 2 divided by 2. Also, I can say this is the absolute values of this. Okay, so I need to put the brackets. What is it? Okay, here we go. I need to cut and yes, I need to cut. Oh, sorry. I need to, yes, here we go. Control X, Control V. Also, I need a space in here. Yes, in here, I need to change the value. Control copy, delete, Control C, Control V. Yeah, our formation should be like this. Okay. I think I need to make it a little bit smaller. Okay. Yes, this is our formulation. Okay, so its strategy is simple. First of all, we also I need to put copy and paste. Yes. Okay. So if the multiplication of the sigma 1 and sigma 2 is greater than 0, okay, its maximum, absolute maximum shear stress is equal to sigma 1 divided by 2. If the multiplication of the sigma 1 and sigma 2 lower than 0, okay, the absolute maximum shear stress is sigma 1 plus sigma 2 divided by 2. Just it, nothing more. It is very simple formulation, okay? So I think let's do practice with the small example 9.7, okay? In point surface, the cylindrical pressure vessel shown in this figure subject to the state of plane stresses. Okay, that's meaning that stresses on 2D case, but we are considering the absolute maximum shear stress in this point. So also, if we consider the third dimension, what is the maximum stress? What is the which value we trying to find the value of the maximum shear stresses on considering 3 dimension. It's very simple. You can see we don't need to calculate to sigma 1 and sigma 2 because also in this example sigma 1 and sigma 2 directly given. I want to say sigma 1 is 32 megapascal, sigma 2 is 16 megapascal. You can see, okay. So its multiplication of sigma 1 and sigma 2 is greater than 0. So absolute maximum shear stress is 2 sigma 1 divided by 2, 16 megapascal. So if you want to try to calculate the sigma 1 in plane, you can see subtraction of the sigma 1 minus sigma 2 divided by 2. This is equal to 6 megapascal. So I forgot to write, I forgot to put the Mohr circle on this example. Also, if I'm trying to show, if I'm trying to add Mohr circle, okay, you can see this Mohr circle easily understand what is the difference between the maximum in-plane shear stress and maximum absolute shear stress. You can see maximum in-plane shear stress and maximum absolute shear stress. Also, some of you think that, hocam, what is the meaning of the 3D stress transformation? Generally, 3D stress transformation is, I don't want to add these subchapter to main section because 3D stress transformation strategy is it's almost similar to 2D plane stress transformation, but you can see in 3D stress transformation to many parameters, many terms added to our 3D stress transformation. So the formulation is becomes a little bit complex. Okay, I don't want to lose time to make practice to see this 3D stress transformation. In order to do give full information, I give a reference in the slide. Okay, also you can see 3D stress transformation. In the 3D stress transformation, I want to show you like in this figure, okay? And this is the general state of stress. You can see sigma x, sigma 1, sigma z, 3, 6 tau xy, about 9 stress parameters, okay? 3 by 3 matrix, okay? In order to convert this system, we are taking a similar, not triangle, not we are taking instead of the triangle, we can see we are pyramid, we are putting in a pyramid, okay? So you can see we are using the direct cosine matrix. I hope you have a information about the direct cosine matrices. We are linear algebra. We are using this term. Each term x, y, and z term direct cosine matrix represented one L1, M1, and N1, and you can see in transformation formulation like this: sigma 1 L1 square, sigma 2 M1 square, like this. This is this kind of formulation. Also, okay, and this is sigma 1, 3 term. These two terms, sigma y prime, sigma z prime, tau z prime. Also, and one more term, I can't remember that 3 term remain. I think that these are related to 3 terms, okay. You can check and you can see these, you can read this article or also references in the book, okay. You can look at and you can try to understand the 3D stress transformation. I want to say strategy, finding strategy is similar, same, but you can see formulation is a little bit complex, so I don't want to spend time. Also, we are not responsible in the book because this chapter, subchapter is not available in our reference book, so I don't want to do this subject in this class. Okay, this is the end of the chapter 9. Okay, thank you for listening to me. See you later.